Welcome to this session of Tech at Lunch. I'm Johan van Noten, and for the past 16 years at Founders Make, I've been busy with several topics concerning model-based systems engineering, model-based software engineering, and also data modeling. Now, during the last several years already, we see that also digital twins become more and more important in the smart industry. And that's why today I would like to present you a session that talks about context-aware digital twin for a smart industry, smart manufacturing. So maybe let's start with a few practical aspects. So please do not record the presentation, and we will be recording it ourselves, and we will use it for sharing afterwards. Also, if you happen to have any questions during the presentation, just use the chat. My colleagues will monitor the chat, will react directly if required, and otherwise at the end of the session, we will handle the open questions. Good. So let's get started. Maybe for most of you, it's not necessary anymore, but anyway, I will give a small introduction on what is a digital twin. And obviously, if you talk about a digital twin, there is also something like a physical twin, and that's typically your production or your product that you're talking about, the things that you are doing in your environment. When you talk about the digital twin, then you typically are thinking about some questions that you want to get answered. For instance, I want to save money, or I want to optimize the quality of a certain step in my process, or the quality of the end product, or whatever. And if you have such a question, you are triggered to create a digital twin. Digital twin, like you see here, what does it contain? Well, typically, it contains some digital representation of your assets or digital representation of your product, and it contains some data that goes with it, or that models that represent those items and that digitally contain information related to your physical twin. On the other hand, it might contain things like some specific data analytics functionality, analyzing the information or simulating what can happen and so on, to do some predictive analysis. That all can be a digital twin. And obviously that digital twin is in some way related to the physical one. And so it will observe the physical twin, and maybe also influence the physical twin to change some parameters, to change some settings, or maybe to intervene in another way. Just depends on your specific use case. On the end user side, or your side, obviously you also want to go and look at that digital twin and see, okay, what conclusions does it draw? Is it still correct? Or if you have a new insight, you want to go and influence the configuration of a digital twin, or you want to add some functionality, or you might initiate some modification in your physical twin, and you might change a process that you have in place, or whatever. So that is what we consider to be a digital twin. Now, let's handle that with a specific example. We will not talk about a full production of a car door, that leads us a bit too far, but we will look at a very small part of it, the gluing of two parts together. So you have a part, and we are then looking at, for instance, these are pictures from our joint material lab, a lab that focuses on the mechanical bonding and tries to optimize adhesives and so on. So the imagery that you see will be from that GML lab. So we say here, okay, take two parts of plastic, and we will see how they get glued together. So in the first step, what they typically do, they use plasma treatment to treat the surface of the piece of plastic. And then they go to the gluing operation, which in this case is obviously a manual one. And it's manual operation. In a real production environment, that will not be so manual. And in the next step, the combined product, and containing two parts, the combined product goes into a curing oven, so it's heated to a certain temperature for some time, and that's how the bond becomes stronger. And then finally, what we typically do is a break stress, and we will test how strong it is, and after some time, with enough force applied, it breaks. and we end up with a product like this. That's obviously not what you want to have in your production. In your production, you will typically do this in 1 on 100 or 1,000 or even less. But for the sake of the example here, it's useful to also look at the measured break stress. So we introduce it this way. So if you look at that kind of process, I think you have a good understanding of the process now. So if you look at that kind of process, you need, let's say, a kind of digitization. You need to have observable values in your physical environment. Otherwise, yeah, you're a bit into the dark. So that is also what we have here. It is quite a digitized process. There are a lot of properties measured or settings collected during the production process, and these are then used in, for instance, answering questions like this one. You might have a quality issue. It seems that your products are breaking too fast, and you don't reach a desired break stress of 8 megapascal. Now, what can you do about it? You want to either increase the break stress, or you would like to correct the appropriate products soon enough in your production process. It makes no sense to do a certain adhesive operation, then go through the full production process, and at the end determine that the product is not good because the bond was not correct. So you want to do that early, and you want to scrap that part early if the bond was not correct, or you want to repair it as soon as possible instead of just waiting till the end. So that is what we will go and look at and see, okay, how can we now relate the break stress to the things that happened already in production? Okay, so we are wondering, can a digital twin help us in answering this question? Well, typically you would create a streaming digital twin, and that's like I explained before. It's observing the reality and the physical twin. It's doing some streaming analytics, maybe showing something to an operator, and then influencing and saying, for instance, yes, this is a good product, or this is expected to be a good product, or no, we think that this product is going to fail, so please do repair or scrap it, depending on the level of the level of the issue. Now, obviously, such a digital twin doesn't just come to be. It has to be created by someone, and a first step in the creation of such a digital twin is collecting historical information, collecting historical data. And so you record the things that happen in your physical twin, and you store it, like, for instance, the break stress test that you did do, or the sensors. I didn't mention them on the previous slide, but the sensors in the environment that collect the humidity or the temperatures, or information from your manufacturing execution system, where you know, okay, at that moment I was creating that product, and so on. That's the information, just the data that you collect, and then you ask a data scientist to look at that data. He will explore that information. He will try to extract the correct information from everything that he sees, and he will try to analyze them, to see whether he can draw any conclusions of what he sees in the data. And after that, he will, in the best case, create some additional insight and say, okay, I will deploy your digital twin, and that digital twin will react like you want it to react. That's the ideal picture. So if I want to start on that, as a data scientist, I would typically ask myself a question like this one: give me all the products that have failed QA tests, and show me the air humidity data during the gluing process step. If I want to do that, then I will first need to look at the ERP databases, because all products, that are all our products, they are to be found in the ERP database. They need to have a failed QA test, so I will need to go to the QA tables and to the tables of our QA systems and find the failed ones there. I need air humidity data. Yes, I know that I do have some time series here or there that contain information about the room sensors. And if I want to take out of these time series those slices that are about a specific gluing process step, then I probably need to look into my MES system to see when did a specific gluing step occur, and then relate it to the time series. You get a picture. So the goal that I'm trying to find will in fact not be nicely presented to me. It will rather be hard work. So that's also what we see at most of the partners that are involved in this kind of systems, is that the data scientist, when he wants to go and do some analysis, that they lose about 80% of their time in just trying to see what data do we have, is it correct, is it clean, how do I get it, because this is in SQL, this is in a time series database, this is still in JSON files or whatever. So it becomes a very awkward job to get the information. And moreover, we see that it just doesn't work that way. You cannot just expect that the data gives you a correct view on reality. If you only look at the data, then probably your insight in reality becomes a bit skewed. And that's also what it was Plato about 2,500 years ago, who said, yeah, as an example for him, and suppose that you lock a man in a cave for all his life, and the only thing he sees is what you see there on the left-hand side, and the only thing that he sees is that is the data. If he now needs to suppose something about reality, probably he is going to go the wrong way. He is going to assume the wrong conclusions. So you will need to give him some additional information, some additional knowledge in order to interpret that data, to interpret what he sees, and that is the context information that we are talking about. And you need to have the correct context. You need to be able to access that context in order to draw correct conclusions on what you see. But still, it is this what data scientists often get offered in our companies. The data is there, so use the data and try to conclude something. And that's where we think that the knowledge graph can provide some assistance and some improvement. Obviously, you need that historical data. No way beyond that. You need to integrate, let's say, the historical data into the full picture, because it's essential information, but it's not the only kind of information. And you also need, for instance, information concerning the type, the thing that you were producing, the parameters, the tolerances that you had foreseen, and things like that. Certainly, and that's what we will also focus on, you need to be able to integrate expert knowledge. And so the information or the data is not enough. You want to add insights that have been previously created, or you want to integrate simulations, and you want to make all that information available in an integrated way. And we see in the knowledge graph as an essential enabler to be able to do that. Moreover, and that's what I just said also, if a data scientist is able to establish some new insight, it would be a pity that the next data scientist needs to redo the job. So you want to be able to insert that new insight also back into the knowledge graph. And so we will focus today on how that knowledge graph, or why we think that knowledge graph is that essential enabler for context-sensitive and context-aware digital twins. Maybe for those that don't know it, I'm not so sure how many people will know this aspect, but if you compare a knowledge graph to a traditional database, or a graph in general to a traditional database, then it's important to see some differences, or to know a few of those differences. And if you look on the left, you have a curing execution, so the performing that oven operation where the material gets cured, and on the right hand side you see a product, and I've drawn exactly the same effect for a graph. Well, the response feel different, but I'll come to that. And so it's a curing and a product. And now you want to see, okay, what did we put into that oven at that certain moment? This curing execution happened at that time, start time, end time, and which products were involved there. If you do that in a graph, then a graph is simply pointing. It says, that curing execution pointing to cured product, that product. That's quite obvious. That's how you think as well. And if you say then one curing execution has done these 5 products, and the next one maybe 3, and the next one 10, or whatever, and then you have just 5 relationships, or 3 relationships, or 10 relationships. In a traditional database, on the other hand, it's a bit artificial. You will say a curing execution is linked to a new artificial table, cured products, where you link that curing ID to a product ID. And you say, for instance, curing ID 1, it's linked to product A, and it has been performing something on product A, and the same curing execution was also handling product B, and so on and so on. You feel that there is a difference in the natural expression of relationships, and it goes all the way. If you're talking about an oven, you had to mention oven ID here. In a graph database, you just point to the correct oven, and it feels a bit simplistic, maybe, this difference, but it's a very important difference if you go and look at the next steps that you want to take, and about the way that you can reason. Another advantage on the graph databases is that it in fact can include, without any structural modification, it can include additional information, like for instance the one that I show now, the last known humidity. Obviously that is just the oven going through the humidity sensor, and that is my humidity sensor, and then to this, the sensor says, oh, these are my values, and then the one with the highest timestamp is the last known humidity. Quite obvious from a reasoning point of view, but quite difficult to store all this additional information in a traditional database. So why do we think that knowledge graph has certain strengths in this context? Well, first, I think I've shown you that relationships are something that a knowledge graph can easily handle. Well, relationships are the future. For instance, if I give you just a number 65, then I give you a number without any context at all, and that's annoying. You don't know what it means. Now I have given you 65 degrees Celsius. You now know at least that it is a temperature, but for the rest you don't know much more. And then you can have other relationships that complete that context. You can, for instance, say, yeah, but oven 7 points to this one as its oven temperature. Then you know that the 65 degrees was an oven temperature. And you could say, there was a curation job in that oven, and that curation job was curing product 27, and then it becomes much more information, a much richer reality than just knowing 65. So the relationships are in fact the context, and that's a very important aspect. On the other hand, relationships important, because just people think in relationships, and that's also why mind maps work so well. It associates, it relates different aspects of what you were thinking about. And the same goes for your company. In your company, you obviously have many silos, many assets, silos like, for instance, the finance department, the engineering department, after sales, and things like that. They all have their own world. Also your assets, if you look at the production, there are a lot of machines there, and you collect information from all those machines, potentially in different databases and so on. You need to be able to relate this information, because many of the questions that you will be asking will handle the different aspects here. And then there's one that looks a bit more into the future, and that's what you have been seeing in the context of IoT and the Web of Things, and then IIoT, Industry 4, and we all heard about these things. And you see that your company will also tend to have more and more relationships to the outside, to suppliers or to customers. For instance, in the linked data initiative, where you can say, okay, but I use information from other companies in order to optimize mine, or even in legislation. If you look at the EU, the digital product passport, which is legislation that obliges you to track a product through its lifetime, and the product is typically not something that you create from scratch till the full end, and you need to track its lifetime through different processes, and also for that purpose you need relationships. So first item, relationships are the future. Now, another aspect for which the knowledge graph is, or at which the knowledge graph is very strong, is the user domain versus the technical domain. Probably doesn't say so much here, but let me put it this way. Suppose that I started today's presentation using this slide. Would you then have understood what I was talking about? I dare to say no, in the sense that this is a potential data structure for what we were doing today. I know that it is not readable, and it's not a purpose, it's a fake data structure anyway. It's about something completely different. But anyway, it is a product structure. It's a production order execution data set. And you see some time series measurements that can represent the room sensor readings and so on. So this might perfectly be the data set that we are talking about today, but you don't understand it. Because first it's not readable, but on the other hand, it's very difficult, it's very technical, and it's technically inspired. There are multiple silos and 3 separate boxes, while in fact what you want to do is to relate things between them. So that is why we say the technical infrastructure is probably not what you want to do if you want to understand a specific domain. No, at that moment, you want to have a user review. And a user review is a thing that we used at the start, where you have the same things and that corresponds in some way. It will correspond to all the underlying technical data, but it uses a representation and the relations that a user understands. And so the data scientist, one of the users, but also your other users in your company, they need to understand the knowledge which is available. Okay, so and that is exactly what that knowledge graph is good at representing things like what you see here in the lower right-hand side corner. Yeah? So that's a second advantage that we see, and then a third one is in fact that the knowledge graph, with its ability to materialize relations, it also is able to explicitize and reuse knowledge. For instance, look at I reduced the complexity now a bit of the process that we were talking about. I left out most of the properties, but if you look here at the break stress, which is measured completely at the end, and someone could go and wonder, is the plasma distance, which is a parameter here in the plasma, in the first step, in the plasma treatment step, is that parameter linked to it? Does the plasma distance influence, in fact, the performance of a break stress? And then I can just start guessing, and I can go and look at data. But the knowledge graph could do better, and the knowledge graph could contain information. Someone has put it in, and it doesn't invent information. Someone has put in information, in this case, for instance, that the break stress from literature, that's why you see the booklet, and that literature describes that the break stress is related to the adhesion strength. If the glue doesn't adhere to the surface of the part, probably your break stress will not be enough. And it also relates to the substrate strength. If your substrate breaks, then probably your break stress is not good enough. In that case, your gluing was okay, but you are using the wrong substrate or the wrong parts. And if you continue with that, you can build a full chain. For instance, here the break stress it influences the adhesion strength, but the adhesion is influenced by the surface energy, which is a physical property of the part. And we know from our own research, we know that we can influence that surface energy by reducing the plasma distance. So if we come closer with the plasma treatment, then this becomes more positive. I'm saying more than what you see on the screen, but that can be included in the knowledge graph. On the other hand, our operators said, yeah, but if we do that, if we make the plasma distance too small, then we overheat. We burn, in fact, the part, so we can't do that either. It's a negative influence. But at least the knowledge graph is able to capture that and to make it explicit and to make it accessible to all people involved. And to certainly to a data scientist who can then see, okay, okay, this is a potential link here. Let me investigate maybe this further, or let me investigate other additional influential properties. It can be contributed by process engineers or data scientists, and yeah, like you see it here, it has a graph or a relationship nature by default, and obviously. And that's what I showed also halfway the presentation. It can be subject to logical reasoning. And the red arrow that you saw here, that's something that the knowledge graph can derive. And if it sees all those links, the knowledge graph also can say, but there is an influence between plasma distance and the break stress. And it can answer you questions like, can you give me all properties that are influential for the break stress? Yeah? So as a conclusion, these for us are the 3 main points, in fact, that convince us about the the strength of a knowledge graph in realizing such context-aware digital twins. Okay, thank you. I'm looking at Seppe now. Seppe, did you see any questions coming in?
Yes, Explore, we have 2 questions. The first one is, how do you see the role of LLMs within the digital twins of tomorrow?
Yeah, can I answer it by asking a question? The acronym LLM is not known to me.
Well, I suggested Thomas is replying to your question, and in the meantime, we just take the following question. What software can we use to create a knowledge graph? How to get started?
Yeah, there are different ways, and a knowledge graph as such, and you could go and look at it very limitedly and just reduce it to just a graph, and then you can start with graph databases. But our experience says that it is not strong enough because you don't have that user domain model behind it, and you will typically want to lift it one level up, and you want to also include some ontology, and then the creation of ontologies together with graph databases, and together with, in most cases, also linking to underlying databases, because that's where your data resides often. And then you need a more complex tooling environment, and there are different ecosystems. And there is Stardog on one hand. Stardog is a solution that tries to integrate most of these aspects into one solution. On the other hand, you have solutions like a combination of GraphDB, OntoText GraphDB, and OnTopic and MetaFactory, which form also an ecosystem that can do that for you. But that's from the knowledge graph perspective. If you want to access a knowledge graph, just like you access, for instance, a SQL database, then it's not much different from SQL. And there is a language, Sparkle, which looks quite a bit like SQL, which allows you to ask, let's say, queries from the knowledge graph, just like you would do SQL if you want to ask for information from a SQL database. I don't know if that answers your question. In the meantime, I see that that someone anonymous answered that LLM is a large language model, and then I suppose you're talking about things like ChatGPT. I'm not an AI specialist, but that's what I link to it at least. Well, we are considering that. We don't know that for sure yet. Like a lot of new possibilities that open when you look at things like ChatGPT. Also, this could influence the way, at least the way that you are storing the knowledge or transferring the knowledge between the human on one hand and the knowledge store below it, because obviously the knowledge here is not a language model, and the knowledge here is something that a human expresses, or the human thinks to know, or a data scientist has found to be true, and you now want to transfer that into a technical system that can capture that information. And I think that is the best opportunity where a large language model might help. On the other side, also when formulating a certain question, and the translation between the question itself, which is then human speech, and on the other hand, the answer of the system, that's also where I see potential link.
Okay, thank you, Johan. There are no more questions, and we are perfectly within the time frame that we have scheduled for this session. So I will give the word back to you to conclude this session.
Yeah, anyway, concluding is mainly just saying thank you. But on the other hand, I would like to also invite you for a webinar that we will host. It will be on the 23rd of June, and probably some sessions follow after that. But the first one is on the 23rd of June. That might be linked to that other question that was asked, how can we get started with a knowledge graph, what tooling do we need, and so on. That's a session in which we will tell a bit more about that, and to which you are kindly invited. You can use your QR code reader to obtain the registration link here from this QR code. So, okay, that being said, I thank you for this presentation, and I see you next time on a Tech at Lunch session. Bye.